Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 18th, 2026, about 6 days ago. It introduces a reinforcement learning framework called Refine that enables fast-weight models to capture long-range dependencies much better by training on next sequence prediction rather than just next token prediction. The paper is titled Reinforced Fast Weights with Next Sequence Prediction, and as we'll see later, the results are really impressive, showing up to a 20% improvement on long context benchmarks. To understand the core difference, let's look at Figure 1. The top panel illustrates standard next token prediction. Here, the model calculates a cross-entropy loss for every single token independently, effectively optimizing just the immediate next step. In contrast, the bottom panel details the Refine approach. Instead of treating every token equally, it first identifies positions with high entropy, or uncertainty. From those points, it generates a multi-token rollout, a short sequence of future tokens, and then assigns a reward based on how well the entire predicted sequence matches the ground truth. This sequence-level feedback allows the fast weights to capture longer-range patterns. Well, having seen the training goal, Figure 2 contrasts the architectures themselves. On the left is the standard transformer. It relies on a global tension mechanism that usually requires more memory as the context gets longer. On the right, the fast-weight model replaces that with a fixed-size memory matrix, labeled W. Instead of storing every past token, it runs an update step to fold new information into W, and an apply step to read from it. This keeps memory usage constant, but it means the model must learn efficient compression, which is exactly where the new training method helps. So, having covered the architecture, Table 1 outlines exactly when this framework gets applied. It lists the standard training lifecycle, starting with pre-training on general web data. But crucially, the authors show that Refine is effective in all the subsequent phases. We see it used in mid-training to adapt the model, in post-training with task-specific instructions, and even during test time training, where the model updates itself on the fly using the actual test data. Alright, while the previous table listed the phases, Figure 3 details the actual 4-step workflow used during training. On the left, steps 1 through 3 show how the model forwards a sequence and uses entropy to identify specific high uncertainty tokens, marked in blue. It then isolates the prefixes leading up to these points. Moving to the right, step 4 illustrates the reward computation. The model generates new rollouts from those prefixes and compares them to the ground truth. The system calculates rewards using cosine similarity and exact matching, which then drive the group relative policy optimization update. Okay, with the training process established, Table 3 presents the performance on long context retrieval tasks. It specifically evaluates the ruler benchmark, testing needle and haystack retrieval across context lengths from 4K up to 16K. The table compares two base models, LACT 760M and DeltaNet 1.3b, trained via standard supervised fine-tuning versus the Refine method. You can see that for both models, the Refine rows consistently achieve stronger results. This is especially visible in the harder multi-key and multi-query columns, confirming that sequence-level supervision helps fast-weight models retain specific details much better than token-level objectives. While the previous table focused on finding needles, Table 4 expands the evaluation to multi-document question answering using the Squad QA and Hotpot QA datasets. The columns on the left track the training strategy across 3 phases: mid-training, post-training, and test time training. Notice the clear upward trend as Refine is applied more extensively. For instance, with LACT 760M, layering Refine into all 3 phases pushes the average Squad QA score from roughly 13 up to 27. So while the previous table focused on specific QA tasks, Table 5 broadens the scope to the full long bench suite, covering summarization, few-shot learning, and coding. It tracks performance for LACT 760M and DeltaNet 1.3b across different training stages. In the LACT section, the average score for standard SFT is just 13.5. However, applying Refine during mid-training jumps this to 16.9. Adding Refine during test time training pushes it further to 18.0, confirming that the benefits compound across phases. Wrapping up, the main takeaway is that standard token-level training limits efficient architectures like DeltaNet. By optimizing for full sequences using reinforcement learning, these models can finally leverage their constant memory to track long-range dependencies effectively. This points toward a future where we achieve massive context windows without spiraling compute costs. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.